Thank you, Francois. So glad to see that people are here this morning. I was a little worried when I saw that France was playing at 11 o'clock last night. And then it was delayed, but here we are. So last time, I outlined some general plan to eventually tell you about two theorems. The two theorems have to do with meshes of maximal entropy and more generally some equilibrium states for geodesic flow on non-compact manifolds and for Sinai billiards. And I outlined one general kind of strategy which has to do with a symbolic coding, taking some Hausdorff measure, using some product structure. That strategy was based on the idea that the MME should satisfy certain scaling properties. And that is the strategy which I will use next time when I tell you about the billiards. Today, I want to tell you about a different strategy which has to do with specification and expansivity. And in particular, how these can be applied in a non-compact setting. Because this is the strategy that we used to prove theorem A, which was the theorem about geodesic flow on non-compact manifolds. So the general result, which I will present today, is joint work with Dan Thompson and Tianyu Wang. And this approach is based on one of the other characterizations of the most familiar MME, which was that it is equidistributed. So the MME for the full shift gives equal weight to every cylinder of length n. And that general principle is the one which we follow to build an equilibrium state, or as I will say it, an MME, in more general settings. So let me start by recalling the story in the symbolic setting. So I'll start by recalling how things work in the symbolic setting to set up notation and ideas. And then I'll say how things work in the setting of compact systems, which are not symbolic. And then eventually I'll say what you have to do in the non-compact setting. So in the symbolic setting, we're going to let A be a finite set, which is the alphabet, and X will be a shift space. So it is a closed shift invariant subset, the space of bi-infinite sequences with entries in A. And for each natural number n, Ln will denote the set of words of length n, for which the corresponding cylinder in the subshift is non-empty. So this is the part of the language that has length n, and then taking a union over all values of n, you get the entire language of the shift space. And this is the notation that I was using yesterday. Capital lambda n will denote the cardinality of the set of words of length n. And then the topological entropy is the exponential growth rate. This is all for a completely general shift space so far, and there is also a strategy for producing a measure of maximal entropy. And this approach goes back at least to Mizurevich. And the idea is that in order to produce an MME, you can do the following. Given a word of length n, you have a measure. Let's call it delta W. And delta W, if you integrate a function phi, just means take the nth ergodic sum of phi. There's a choice to be made here. You pick some point in the cylinder. So if I were going to really be completely correct about this, yes, I suppose it should be, shouldn't it? Thank you, Anthony. Yes, we average. I might even have said average. I might not have. So you pick some point in the cylinder, and you just do the empirical average along that point. And then you let μn be the average over all words of length n of the corresponding measure. This gives you a sequence of probability measures which gets closer and closer to being invariant. And if you pass along some subsequence, you get some measure mu which has maximal entropy. And this is a very general fact. This is the strategy behind Miserevich's proof of the variational principle. So this is a construction based on the equidistribution property of the simplest instances of measures of maximal entropy. So now we want to talk about under what circumstances you can show that this is the unique measure of maximal entropy. One way to do this is if you have the specification property. So the shift space has the specification property if the following is true. We want there to exist some time, tau, which is a natural number, with the property that for every pair of words in the language, you can find a word of length tau that connects them. So it's a mixing property, but it's a uniform mixing property. If you have a topologically mixing subshift, then a word u like this always exists, but you don't necessarily have control over its length. If you have a topologically mixing subshift of finite type, then you have this property, but this is more general than being a mixing SFT.
Sorry, what is your restriction on u?
It has length tau. So the length of u does not depend on the choice of v and w, and that's the crucial feature. So this is the specification property in the symbolic setting. In the non-symbolic setting, it will look, it takes a little longer to write down the details. But the consequence of this is that if I look at this sequence, capital lambda n, the number of words of length n, and I want to know how many words are there of length, length n plus k. Well, there is a submultiplicativity property. The number of words of length n plus k can be at most the number of words of length n times the number of words of length k. This is immediate. It doesn't require specification. What specification gives you is a super multiplicativity property up to some constant. So the number of words of length n plus tau plus k is at least this product, because you can take any word of length n and join it to any word of length k by putting tau symbols in the middle. This set of inequalities is enough to guarantee what last time I called equation 1, or property 1, which is that the number of words of length n is within a multiplicative constant of e to the nh. So this was my property 1 from last time, that the exponential growth rate, there in the box, defining the topological entropy, actually becomes these uniform counting bounds. And this was the first essential ingredient in the list of 3 properties that I mentioned last time, which you want to establish in order to prove some uniqueness result. So it's a start. The next thing is to show that once you have these uniform counting bounds, you can use these together with the specification property to study this Miserevich measure. And show that it has a Gibbs property. I'm going to put a plus there because it has a strengthened Gibbs property. So last time, I wrote this down as property 2. which is that for every word of length n, the measure of the corresponding cylinder is within a multiplicative constant of e to the minus nh. This is what we call the Gibbs property. And I said that a strengthened version of it also holds. If you want to know the measure of the set of points which sees a particular word now and then a specified word w a little later on, you can also get this bound. This is, let's say, greater than or equal to, no, it's within a multiplicative constant, so let's call this, I don't know, C1. This should have been plus minus 1, similarly here. V to the minus k plus n times h. And this is what last time I referred to as 2 plus. So it's a sort of second order Gibbs property. And it's like, it's in, well, at the top one is as high as it will go, but is that better? Okay. So, yes, please. Yes. Yes, so eventually then the theorem is that as soon as you have specification, you get this measure as Gibbs. But yes, yes, for any mu obtained as a limit of this Mizurevich construction, you have the Gibbs property. And so yes, you are correct that 1 is of course a consequence of specification. I write it this way because you use 1 in an essential way in this proof. You use it repeatedly. Thank you. Thank you all for keeping me honest. I think it's correct now. So this is most of the story in the symbolic case. Last time I listed 3 properties that come into play. There's one more, which is this uniform Katok bound. So let me mention that, and then I can say something about non-symbolic. Last time I made this definition that if you have some ergodic measure nu, you want lambda n nu to be the smallest number of n cylinders that are required to have weight at least 1/2 with respect to nu. And using property 1, one can prove that, in fact, lambda n mu is greater than or equal to some constant times e to the nh for all measures of maximal entropy. Actually, you don't need it to be ergodic. So whether or not it is ergodic, if you have an invariant measure of maximal entropy, it satisfies this property. That I think is the probably the least obvious argument of any of the ones that I've mentioned so far. It takes a little work. And then another not immediately obvious argument is that if you put properties 2 plus and 3 together, then you can conclude that the Mizurevich measure mu that you built is the unique MME. Keith. Here. It's the one after 2. Whether or not I labeled it. Okay. So, this is the plan. This is a complete proof in the symbolic setting. Now I want to tell you how it goes to the non-symbolic setting, and then I want to explain what we have to do to push it to the non-compact setting. So now instead of a shift space, let us consider a compact flow. That is, we have some compact metric space X, and we have some continuous flow on that space. So I want to give the ingredients to extend this story. So there's a family of metrics now. Family of metrics is the following. Given some number t, we say that dt of xy is the supremum of the distances between their orbits. So you take the point x, the point y, you flow both of them forward for time s, where s is something between 0 and t. You compare their distances, you take a supremum, and this is the dynamical metric or the Bowen metric of order t. And then in this metric, we have a family of balls, which are the Bowen balls. And in this non-symbolic setting, it's not enough just to have specification, which I haven't even defined yet. One also needs a certain expansivity property. So the expansivity property is the intersection over all positive values of t of the, this capital gamma is the bi-infinite Bowen ball. So it is the set of points which shadow, whose orbit shadows for an infinitely long time, both forwards and backwards. Now, specification, but expansivity. The expansivity property is the property that this bi-infinite Bowen ball is contained in a small piece of the orbit. So I probably should have put some quantifiers here, as I always tell my grad students they should. I should say that there exists an epsilon and an alpha such that this is true for every x. So you have some expansivity scale epsilon. If two orbits remain within distance epsilon for all time, forward and backward, then one of them must in fact, well, they must in fact lie on the same orbit, and the time between them is small, at least uniformly bounded. So this is the expansivity property. There exists an epsilon, yes, I will write it. So at scale epsilon. So epsilon is fixed, and then this should hold for every x. Now, we come to the specification property, which I have no desire to write down a full definition of. Let me write down some kind of hybrid definition. The definition of specification in this setting is that for every scale, let's say rho. Rho is what we do in the paper. For every rho greater than 0, there exists a tau greater than 0, such that if I choose any sequence like this, so here, xi is an element of the space, and ti is a time. And I want to think of this pair as representing an orbit segment. It represents the orbit segment that starts at xi and moves for length ti. And this is the point at which I can either write a very complicated formula or draw a picture. And the picture is like this, that you have your orbit segments. And my picture is misleading, as all pictures are, because there's no restriction on the length of these. Of course, I'm starting to draw them as if they have the same length. And the game is that inside each of these, if you take a little row window around each of them, or draw a tube of width rho around each of these, you can find a single orbit that connects them, except it should do it in the order you specified. And if I say nothing more, that is the topological mixing property. So it should connect them, and all of the transition times should be equal to exactly tau. So you can specify exactly how long it takes to go from each one to the next. So this is the specification property. And the theorem due to Bowen is that specification plus expansivity for a compact flow. For a compact flow, it's due to, it was written down by Franco, Bowen's student. Bowen did it for discrete time. Yes? Equal to. There are different versions of the property. For the current discussion, let us say equal to. If you have less than or equal to, you can make things work. It's just messier. Yes, and I think they also allowed a little bit of wiggle, but just a little bit. But which is why you don't actually need the wiggle that they allow. Yes. So those are definitions. Now, we want to recreate the story from the symbolic setting. How do we do it? There are three things we need. Well, 3.5, depending on how you count item 2. You need uniform counting bounds. But what are we counting? Lambda n was the number of words. Here there are no words. It's a smooth system, or at least not symbolic. Next, you need Gibbs bounds on the measure of cylinders. Here there are no cylinders. Similarly in 3, this is in terms of words and their corresponding cylinders. So all three of these properties must be reformulated in the non-symbolic setting. And here's how it goes. For item 1, so here I want to allow k to be arbitrarily large. If you are in this, this is a worth saying, since you will notice a discrepancy between the way I formulated it for symbolic systems and here. For symbolic systems, I just said you need to be able to put two things together. But of course, in a shift space, as soon as you can put two things together, you can iterate the process. Here, you can't iterate the process in the same way, because if you shadow the thing which shadowed, then the triangle inequality would say now you shadowed to within 2 row, and then 3 row, and then 4 row, and unless you have some, if you have some exponential convergence, then you can make it work. And this is how one proves that, for example, and I probably should have said this, a no subflows satisfy the specification property. And it's proved by that kind of iteration procedure. The issue is that here it's an ultrametric, not just a metric, so the triangle inequality is rather better. So there were 3 properties. First had to do with the counting bounds. And so what we do here is we change the definitions. And instead of counting number of words, which doesn't make sense here, we say that lambda n of epsilon is the largest cardinality of a set E in the space X that is, this should not be n, this should be t, because we are in continuous time now. I said it's a flow. This set should be t epsilon separated in the sense that for every pair of points in E which are not equal to each other, the distance between them is greater than epsilon. And so if you make this your definition of lambda t, then it makes sense to ask for property 1 to be true, and in fact it is true, and the proof is largely the same as this, modulo some annoying technical details about scales which I will not inflict upon you. So then we come to property 2, the Gibbs property. You can build a measure of maximal entropy following Miserevich's idea using epsilon separated sets like these. There's a new issue here, which is making sure you can pick a scale at which all of the entropy appears, and that's guaranteed by expansivity. And the bound that you need for the Gibbs property here, instead of looking at a cylinder, we look at these Bowen balls. So the Gibbs property takes that form. You modify the other Gibbs property in an analogous way. And so far everything is very, more or less, you kind of do the obvious thing, right? You modify the definitions in a way that is, I think, fairly natural, although I've been staring at these for long enough that perhaps things seem natural, which were not originally so. But number 3 is messier. So number 3 was this statement that for every collection of words whose cylinders have uniformly positive weight with respect to some MME, there's a uniform lower counting bound. And if I want this in the non-symbolic setting, now I need to do something non-obvious. I need to work with adapted partitions. So, a partition psi t will be called adapted if the following is true. So psi t is some partition, it will in fact be finite, of my space X. I will denote the elements of the partition by Wi. You should think of them as being analogous to the words, which we had in the symbolic setting. Each of these partition elements should have the property that for each I, there exists some point xi such that the partition element, which may have some strange shape, contains a Bowen ball of radius epsilon and is contained within a Bowen ball of radius 2 epsilon, so of order Ti. Ah, yes, I have a machine that can do this for me. So this is sort of an annoyingly technical condition which generally I wouldn't bother bringing up, except that it actually will play an important role when I describe the challenges that one is faced with in the non-compact setting. But in the compact setting, once you make these definitions, you can run this same argument and, briefly speaking, everything works and they all lived happily ever after, until they decided to think about non-compact things. Ah, yes, thank you. I'm getting ahead of myself. In the non-compact setting, I will need to consider something where those TIs can in fact be different. But for now, yes. In the compact world, everything is nice, and that's just the same T for all of them. Thank you very much.
Substantially different from asking that you can make a covering Bowen ball that has a fixed amount of overlap?
I mean, the way that you generally do this is you take a covering by Bowen balls of order 2 epsilon, where the centers are sufficiently separated, and then you just use some greedy algorithm. I'm not sure exactly how it relates to kind of Besicovich kind of covering stuff. So yes, you use this adapted partition, and then you define lambda n nu in the same way, except that instead of dn being a collection of w's, which are words, now it is a collection of w's, which are elements of the partition. So are we all happy with the compact setting? Because now I'm about to make you unhappy. So we go to the non-compact setting. So in the non-compact setting, I want to consider the following. I want to have a complete metric space in which closed balls are compact. But the space itself may be non-compact. As I suggested last time, the motivating example here is that of geodesic flow over a non-compact manifold, and so the phase space in that case would be the unit tangent bundle. Ft will once again be a continuous flow. And well, what's the idea? The idea would be to take all the definitions we just made up there in the non-symbolic setting, use those definitions, and produce a theorem. The problem is that things break immediately. Things break immediately because if you look at lambda t, which is how many of these epsilon separated points you can fit in your space, well, it's non-compact, so it's infinitely many. So immediately, lambda t is infinite. This is, of course, exactly the same problem that you run into if you want to do thermodynamic formalism on, say, a countable state Markov shift. And I should say that a tremendous amount of our approach is inspired by exactly that theory, the development of thermodynamic formalism for countable state Markov shifts, which only Sarig worked out. Also, Malden and Urbanski have a treatment of this. And we borrow a lot of ideas from that, although the techniques are ultimately rather different. So if you want to make lambda t finite, you can do the following, which is completely analogous to what is done in the symbolic setting. I'm going to let script r denote the collection of compact subsets of the phase space with the property that the interior of A is non-empty. And I think of these as reference sets. This is why I use the symbol R. So we have these reference sets. And given a fixed choice of reference set, I want to define lambda t as follows. I'm going to let A subscript t denote the set of points which are currently in A, whose orbits also return to A after time t. So you have your set A, you have a point x, it goes off and has fun out in the world, and then eventually it comes home. it could come home in between, and perhaps I should make that clear. It's not that this is the first return time or anything else. It's just that at time t, it happens to be there. Now, we make the following definition. The entropy with respect to the reference set A is the limit as epsilon goes to 0 of the exponential growth rate of this lambda t, except that that lambda t up there, wherever it was it? There, immediately above me. That lambda t was the maximum cardinality of an E which was a subset of X. Here, I am going to require that E is a subset of AT. So what this quantity means is the maximum cardinality of a set E such that E is a subscript of AT, and it is T epsilon separated, where T epsilon separated means exactly what I wrote previously. So this is a definition of topological entropy with respect to this reference set. Omri refers to the analogous thing in the symbolic setting as the Gurevich entropy. In our paper, we refer to this as the Gurevich-Sarig entropy, and there is a corresponding notion of pressure, which I will not discuss. And then the topological entropy of the whole flow is simply the supremum over all reference sets of this quantity. So last time I wrote theorem A on the board, and I circled in red 4 different things which I promised I would explain or define. 2 of those were HA and H top. So I said that we had a variational principle involving certain quantities, which I had not explained yet. These are those quantities. So the first part of the theorem is that there is a variational principle involving these. So there is a variational principle. Under the assumption of specification. Now, of course, I'd better say what specification means. Because the definition that I put for compact spaces is certainly too restrictive to expect in the non-compact setting. Because I can have points in the non-compact setting which are arbitrarily far apart. So there's absolutely no hope to have a uniformly bounded transition time tau that's going to apply to all sequences of orbit segments. So the appropriate specification property in this non-compact setting takes the definition above and says the following. For every reference set A and every scale rho greater than 0, there exists a transition time tau, which is allowed to depend on both the reference set and the scale, and which has the property that for every sequence of orbit segments, with the property that the orbit segment looks like the one I drew over there, things work. And then the rest of it is the same as before. So the crucial difference is that you do not require arbitrary families of orbit segments to satisfy this property. You only require it to hold for orbit segments which start and end inside your reference set. Rho is the shadowing scale. It's how close you must approximate the orbits. Yes.
I'm sorry.
Yes.
The points that we're taking are different ATI, but each ATI gives a different tau. So what is that?
The same A. A single A.
Oh.
So.
Oh,
You fix a single reference set, and then you consider some sequence of orbit segments which start and end inside this same reference set. So this, yes.
So assuming this specification, you get the variational principle.
Yes.
Isn't it a bit strong?
Probably.
Usually, the variational principle is known in much.
Yes. I make absolutely no claim that this is any kind of optimal hypothesis to get a variational principle. The fact is, the variational principle is not the thing we are interested in. What we are interested in is the uniqueness result.
Do you have some idea of what?
No.
Good condition, what a good condition?
No, I have no idea.
When you say variational principle, you mean the classical one, the hyperbolic quantities, the supremum?
Yes, is the supremum of the measure theoretic entropies. Handle kitchens is something else. I think it's a different, I think their definition of topological entropy is not exactly this definition. So then I think it becomes a question of whether this topological entropy agrees with theirs. This is the problem with making definitions like this. They sound general. Maybe I should say, here. The Gurevich-Sarig entropy, which is not a priori what is defined somewhere else. Now, then there's the question of whether their topological entropy agrees with this one, and that I don't know about. Yeah, I know we thought about this at some point, but I think Dan was more aware of it than I was, and so whatever he just said. Yes, Keith. Oh, do I have to? Okay. All Borel probability measures, invariant ones. Yeah. Yes, you are, yes, so, okay, fine. I will be precise. There. Yes, so one of these quantities you can kind of make sense of before I even start talking. The other two I have to define. Yes. That's because of the specification property. Yeah. Yes, probability measures. Now, so far, I've taken nearly all of my time, and all I've accomplished is to formulate some definitions and say kind of the initial step. And so far, there are no real surprises, just annoyances. So here's one thing that was a surprise to us, at least. So if you're expansive, then you can remove the limit here. You have that, I think you have to take this to be half your expansivity scale or something, but the quantity that you get without this limit is, in fact, all of the entropy. And this is an essential step. The whole construction that I outlined in the compact non-symbolic setting relies on being able to work at a specific scale. And so, it's very good to be able to work at a specific scale, and as long as you're expansive, you can do so. Our motivating example was geodesic flow and negative curvature. And in the compact setting, this is nice and expansive. Yeah, probably. This was meant to be sort of the second part of this theorem. So you have specification, then you get the variational principle. If you add expansivity, then all of the entropy appears at a fixed scale. So now here is a problem which arises in the application. So the geodesic flow on a negatively curved surface with cusps is not expansive. And in fact, a paper working this out in full detail appeared on Archive not so long ago. The idea, the reason, one way to see that there may be an issue is that expansivity for geodesic flow is often connected to the injectivity radius, and the injectivity radius goes to 0 along a cusp. But the way to argue that there is a real problem is that if you have some geodesic which goes up into the cusp and then comes back, it turns out that you can, through suitably clever arguments, approximate this with a geodesic that winds around the cusp an extra time before it comes back down. And that you can do this so that these two geodesics are within scale epsilon in the sense of that expansivity property up there. So this would create a problem for our application. Now, so I will endeavor to finish this in something resembling my allotted time. I want to give the idea behind how we resolve this, and then next time I can say something about the rest of the argument. So you have your manifold M, on which you do a geodesic flow, and you have its universal cover. The family of metrics in which this is not expansive is the one defined up there. Let me refer to this as the Bowen family of metrics. And this is the following. You take a supremum over times between 0 and t of the distance between the two things you are flowing, which amounts to taking an infimum over all of their lifts to the universal cover of the distance there. So here, d represents distance in the universal cover. So you have 2 unit tangent vectors. This is the dynamically defined distance. What we do in the paper to deal with this example is we use a different definition of distance in which these two things are reversed. So we take an infimum over all lifts of v tilde and w tilde of the supremum. So in other words, another way of thinking of this would be that you are taking the dynamically defined metric in the universal cover rather than on the manifold itself. However, this creates a problem when you want to run the specification and expansivity machinery, because that is all written down with respect to the usual family. I'm sorry? These are compact. Yeah, but you take any lifts, then this supremum will be finite by compactness. So it's always finite. Yeah. So this family of metrics has the following property. It has the properties that if I take the distance at time s plus t between the corresponding orbit segments to v and w, and I compare this to the maximum of the distance through time s and the distance in the second part. For Bowen's definition, these are always going to be equal. For this definition, you don't get equality, but you do get an inequality. So that's item 1. Item 2 is that for every compact A, In fact, for every compact A, yeah, let's just say it like this. There exists an R greater than, which depends on A, which is greater than 0, such that if the following is true, if V lies in A, if FSV lies in A, and Fs plus T, V lies in A, and if the distance between, if this one, the distance is less than R, then we have equality. So let me interpret this mass of symbols and then I will stop. So the idea here is that you have two orbits. Say this is the orbit of V, and this is the orbit of W. And if you want to compare how close these are, you can look at time 0, time S, time S plus T. And if all you're ever doing is comparing the pointwise distance, then the distance of the whole things is the maximum of these two, and there is no problem. The property that this family has is that it's always greater than or equal to, but it could be strictly greater. However, if it happens that, actually here, if it happens that this is in A, and actually for these purposes this is enough, you don't need this business about the other endpoints. And if this is less than R, then everything works the way you expect it should. So we call this the property of being a coherent family of metrics. We started off with dynamically coherent, but we decided it would be too confusing, so now they're just coherent. And everything in our general machinery, which I'll talk more about next time, is built around coherent family of metrics rather than just the specific Bowen family. And the benefit of doing this is that that definition of expansivity works for this sort of geodesic flow with respect to this coherent family of metrics. And so then we can apply the whole machinery, which I will say something about next time. But that's all for today. Thank you.
One quick question now. Really